Hi everyone, welcome to this module of the MOOC about table constraints. So, what is a table constraint? A table constraint is an enumeration of all the possible assignments for a given number of variables. So, for example, here you have 3 variables and you have a table which enumerates all the possible assignments. And the solution of this constraint is thus one of these assignments. Table constraints are what we call extension formulation of a constraint. In comparison, intention formulation are, for example, all different, where we have a formula that expresses the solution of the constraint. So if we have a formula, we can just check if the formula is correct. But for extensional formula, we just have to list all the solution, and to check if a solution is part of the constraint, the solution needs to be in the list of the solutions. The table constraint is one of the most flexible constraints in the universe. Why? Because we can turn any constraint into a table constraint. So you can turn any intentional constraint into a table if you want. You just have to list the solution. So for x plus y equals z, you just list the solution, you have a table. You can also do it for all different, it's also possible, but you can also express more difficult constraints such as this one, which is something, but you can express it as a table. You just need to enumerate all the solution and you got it. So now let's have a small example with the Enigma machine. So everyone knows about the Enigma machine. It was a cryptographic machine that was used by the German during the World War II. What was given, we had an input, which was a text, which was passed through some routers, which was encrypting the text into an output. And the British, what they needed to do, they had the output and they had some part of the input, but not all the input. And what they wanted to find, it was all the input, but also the settings of the Enigma machine. And in fact, the Enigma machine, you can turn it into a CP problem. You can see the article cited here on how Turing and Singleton R consistency broke the Enigma code, if you want more information about it. But the main component is the modulo constraint. And the modulo constraint, in fact, you can turn it into a table. So let's look a bit at what we did, they did in their paper. Well, let's focus on a simple case. You have only one rotor. The rotor is here. And the rotor, it has a given setting, which is the wires that take one input and turn it into one output. So the thing is, at each step, the rotor here, the part of the rotor with the input, will slide a bit. So here, you see after one step, it has slide from 1, and then at step 2, it has slide from 2. But the setting is not changing. So what is happening is that the input corresponding to a given output is changing at each step. So how are we going to model this? Well, in fact, the wires, they correspond to a mapping between a position, an input position, and an output position. And what do we need to have is what is now the input position of our letter in the input. And the input position of the letter is the letter at the initial position plus a shift modulo the number of inputs that you can have. So here, at step 1, we have input 0, it goes to 2. At step 1, you have input 3, which now is shifted there. So it corresponds to, in fact, 3 plus 1, 4, modulo 4, so position 4 here. And then step 2, you have input 4, which with a shift of 2 corresponds to 6, modulo 5, so it's 1. So position 1 of input, here you have 0. And so how do we model this as a table? Well, you can just list all the solutions. So you will just enumerate all the values for all of the inputs and just compute what is the correct output, and you have your table. And now you can input it into a CP model to solve the Enigma machine.